This presentation is about solar calorimeters, their application, properties, uncertainties, and calibration. Solar calorimeters are used to measure concentrated solar power through a point-focused solar concentrator. Power, also known as the rate of heat transfer, is the quote-unquote measured variable. Rate of heat transfer cannot actually be measured, so instead we calculate it from other measured variables. There are many different types of solar calorimeters. In this presentation, we will look at a simple calorimeter consisting of a body which separates the system from its environment, a piping system where water flows through, a solar concentrator, and a temperature measuring device. In our example, we will use a rotometer for measuring flow rate of water and thermocouples for measuring temperature. The equation for solar power is Q dot S equals m dot times Cp times T out minus Tn, where Q dot S is the solar power produced from the calorimeter, m dot is the mass flow rate of water through the calorimeter, Cp is the constant pressure constant, T out is the temperature of the water leaving the calorimeter, and Tn is the temperature of water entering the calorimeter. The point-focused solar concentrator is made up of plates that absorb solar radiation at its inlet. As water flows through the concentrator, heat is absorbed from the concentrator and removed from the calorimeter. The temperature of water is taken at the inlet and outlet, providing values for Tn and Tout. The rotometer is used to measure the volumetric flow rate of water passing through the calorimeter. Volumetric flow rate is used to find mass flow rate, discussed later in the video. Cp and density, which is used to calculate mass flow rate, are found from tables using atmospheric pressure and the recorded temperatures Tn and Tout. The first source of error that will be discussed is undesirable heat transfer. Undesired heat transfer can be heat transfer from the concentrator to the surroundings instead of to the water as desired. Undesired heat transfer can also come from the water itself, either to or from its surroundings after being heated and before the temperature leaving the calorimeter can be taken. This can be avoided by using proper insulation and by using thermocouples to measure the lost heat in order to account for it in the final calculation. Another source of error is the size of the calorimeter. The larger the calorimeter, the longer the water must travel in order to reach where the output temperature is recorded. This causes there to be a longer response time between when the water first enters the calorimeter to when it leaves. This means that larger calorimeters are exposed to more undesired heat transfer within the system and are subject to time delay. Flow rate of water can also be a source of error in the solar power measurement. Higher flow rates reduce the temperature difference between inlet and outlet. If water is not exposed to the point-focused solar concentrator long enough, the water passing through the calorimeter is not sufficiently heated, causing the solar power measurement to be biased to be low. This is because there is not enough time to let the heat transfer take place between the concentrator and the water. If the flow rate is too low, significant heat transfer can occur from or to the surroundings as water flows through the piping. The calorimeter is not what is actually calibrated. Instead, the measuring devices used to gather values for variables in the solar power equation are calibrated. The measuring devices we chose for this calorimeter that require calibration are the rotometer for flow rate and thermocouples for temperature. The rotometer is used to find mass average flow rate. To do so, the volumetric flow rate can be found by reading off the value on the rotometer. Once the volumetric flow rate is found, it can be multiplied by the density of the water mentioned earlier in order to find mass flow rate. The rotometer should come with the manufacturer's instrument uncertainty and calibration data. However, if you want to do your own calibration, there are a few things you must do. You must use an alternative, more precise flow rate measuring device as a standard. An example of this would be a wet test meter. Once you find the flow rate from the rotometer, you must use uncertainty analysis to compare the results you get to that of the standard device. If the results are within an accepted range, the rotometer may be used for the calorimeter. A thermocouple is used in order to find both the inlet and outlet temperatures of the water. A thermocouple is made up of two dissimilar metals, a junction, and a voltmeter. Once again, a manufacturer should provide instrument uncertainty and calibration data. For type J thermocouples, the most common type of thermocouple, instrument uncertainty can be as low as plus or minus 0.1 degrees Celsius at a 95% confidence interval. It is important to note that for thermocouples, the input to the system is temperature and the output is voltage. The voltage is measured between the two metals. The difference between the input and output voltage on the voltmeter is called the EMF. The EMF is used to look up the temperature values on a chart, or in a data acquisition system where the output is converted to a temperature value. The temperature value is then used in a heat transfer equation. If a data acquisition system is used, note that due to a bias correction in the system, there is a systematic error usually ranging from 0.5 to 1.5 degrees Celsius. It is also important to realize that there are some physical errors caused by the solar calorimeter that could affect the results from the thermocouple. These include insertion errors, conduction errors, and radiation errors. When the thermocouple probe is inserted into the calorimeter, there is a risk of conduction taking place between the water and the surroundings. This would be reduced with proper insulation. A radiation error can occur based off of the fact alone that this is a solar calorimeter and the radiation from the sun could affect the thermocouple if there is exposure to the probe. This can be minimized, however, if radiating shields are used to reduce the probe's exposure to the sun. Once the uncertainties are found for all of the measuring systems of the calorimeter, they can be propagated to get the uncertainty for the heat transfer of the solar concentration panel. This is a simple solar calorimeter, and in many cases, there will be many more variables in the uncertainty analysis. For our example, we show the equation to find uncertainty of the rate of heat transfer from taking the uncertainties of the temperature and mass flow rate. Then multiply them by the partial derivatives of the original heat rate transfer equation and take their Riemann sum square to calculate an overall uncertainty. Once again, this is only a simple example of a solar calorimeter, and there are many versions with different properties to improve their systems, which all lead to more variables and more uncertainties. Thank you for watching our presentation on solar calorimeters. We hope this helped broaden your understanding of the application, properties, and calibration of the system.